The diesel engine has long been known as the most economical and efficient power plant for helping man extend his limited physical powers to provide food and comfort. Diesel engines are equipped with a fuel injection system which delivers fuel to the combustion chamber and is responsible for controlling the engine speed and power output. One of the most popular fuel injection systems is the Stanadyne rotary distributor type, built by Stanadyne Diesel Systems. Through manufacturing licensing agreements, diesel injection pumps incorporating Stanadyne's design principles are made throughout the world. Millions of small, high-speed diesel engines are in service incorporating Stanadyne injection pumps. Every piece of machinery conceived by man will eventually require service to ensure that the machine operates economically to maintain profitability. As a diesel engine ages, so does the fuel system. Fuel consumption and exhaust smoke levels may increase. As efficiency falls, profitability will drop. In order to properly service any diesel fuel injection system, a thorough and complete knowledge and understanding of its operational principles are required. The diesel fuel injection system is required to produce extremely high fluid pressures and precisely timed delivery of the fuel charge into the engine cylinders. Regardless of brand, fuel injection system components contain the most precisely machined parts that can be made by man and production machinery. Extreme care should be exercised in handling, storing, cleaning, and repairing of these delicately machined components. The Stanadyne fuel injection pump differs from other systems in that a common set of pumping plungers is combined with a rotary distributor to measure and deliver equal amounts of fuel to each nozzle and cylinder of the engine. The rotary distributor directs the high-pressure fuel charge from the pumping plungers to each cylinder in engine firing order. Other makes of fuel systems utilize one pumping plunger and cam for each of the engine cylinders. The rotary distributor principle reduces the number of like components in the pump and at the same time ensures even distribution to each cylinder. A typical Stanadyne pump is gear-driven from the engine gear train and is mounted at the rear of the gear case. The drive shaft incorporates a tang and slot connection to drive the distributor rotor. The rotor carries the pumping plungers, shoes, and rollers. Surrounding the head of the rotor, the internal cam ring drives the plungers through the rollers and shoes to develop the injection pressure. The governor weight retainer and governor weights are mounted on and driven by the rotor. The governor thrust washer and sleeve are inside the governor weights and ride on the drive shaft. Changes in throttle position, engine speed, or load result in different commands to the metering valve from the governor. The throttle shaft lever, governor spring, governor arm, and linkage hook assembly position the metering valve to satisfy the power demand placed upon the engine. The transfer pump and pressure regulator are at the rear of the injection pump. The head outlet fittings, hydraulic head, and distributor rotor comprise the high-pressure portion of the pump. The rotor carries the delivery valve spring, and stop. An advanced mechanism is at the bottom of the pump. It is a simple hydraulic mechanism used to rotate the internal cam ring to vary injection timing. One of the functions of the transfer pump is to draw fuel from the fuel tank through a series of fuel filters to the pump. A portion of the fuel is returned to the tank for cooling and deaeration purposes. Fuel is drawn through a fine filter screen into the inlet of the transfer pump cavity, where a vane-type transfer pump rotating in an eccentric liner draws fuel from the tank. As the pump rotates, fuel is carried around to the discharge side, where the decreasing volume pressurizes the fuel and forces it to flow out of the pump. The transfer pump discharges to the injection pump and the pressure regulator. The regulator in the discharge circuit consists of the regulator sleeve, piston, spring, and adjusting screw. Changes in engine speed or load causes the fuel requirement to change in the engine. The pressure regulator automatically provides a constant pressure for a given speed and load by bypassing a portion of the transfer pump discharge. Bypass fuel is returned to the inlet side of the transfer pump. The pressure regulator also provides compensation for the differences in fuel viscosity by use of a small orifice located in the pressure regulator adjusting screw. Increased piston leakage due to lower viscosities will cause a pressure rise in the regulating spring area. The pressure increase assists the regulator spring in moving the regulating piston to preserve the correct transfer pump pressure. Fuel pressurized under control from the pressure regulator flows through the hydraulic head. An automatic air bleed system is incorporated in the Stanadyne pump. It consists of a vent wire inserted in an orifice provided in the transfer pump outlet. Air entrained in the fuel collects at the highest point in the head and escapes past the vent wire, through the outlet hole in the hydraulic head, into the governor cavity, and finally returns to the fuel tank through the pressure regulator in the top of the pump. Fuel pressure from the transfer pump is used to power the advance mechanism and to supply flow to the transfer annulus around the inside of the head to the metering valve. The metering valve controls fuel flow to the pumping plungers and the engine. It is rotated mechanically by the governor, the linkage hook, and throttle mechanism. As a charging port in the distributor rotor comes into alignment with the charging port in the head, fuel under pressure from the metering valve and charging annulus flows through the charging port in the rotor, through the bore of the rotor, and into the space between the plungers. During the charging cycle, the pumping plungers and their shoes and rollers are passing through a valley of the cam to permit the plungers to be displaced by a volume of fuel proportional to charging pressure. With the pumping plungers charged and the charging ports sealed, the charging cycle has thus been completed. As the rotor continues to turn, the discharge ports between the head and rotor come into alignment. The rollers contact the ramp of the cam, driving the plungers inward to develop the high injection pressure. Fuel now under high injection pressure is displaced by the pumping plungers. It flows through the bore of the rotor and out of the discharge port to be distributed to an individual cylinder. Injection through the nozzle into the engine cylinder is occurring while the rollers climb the cam. Injection ends when the rollers reach the peak of the cam lobe, thus permitting line pressure to drop and the nozzle to close to promptly terminate injection. This is the secret of the Stanadyne distributor principle of alternate charging and discharging to each cylinder. The common set of pumping plungers deliver fuel at high pressure through the rotating rotor to provide the distributor action utilized in the Stanadyne pump. To complete the distributor action, fuel delivery from the pump is in the proper rotary order, but the fuel lines are led to the engine cylinders in firing sequence. A delivery valve is incorporated within the rotor to provide an abrupt end to injection and to control line pressure to prevent secondary injections. High-speed diesel engines utilizing cam-actuated injection systems suffer injection and ignition delays at high rotative speeds. Delivery from the injection pump to the inlet end of the fuel line generates a pressure increase which requires a finite amount of time to reach the nozzle end of the fuel line. The small increment of time delay measured in milliseconds becomes significant at high engine speeds. To overcome these inherent delays, it is necessary to advance the start of delivery in the pump so that delivery to the nozzle occurs at the optimum time. Advancing the beginning of pressure rise and start of fuel delivery is easily accomplished in the Stanadyne pump. Transfer pump pressure, which is related to engine speed, is used to power a hydraulic mechanism to rotate the internal cam ring a few degrees opposite pump rotation. As the cam rotates, the rollers will contact the cam lobes earlier with respect to the discharge port on the rotor, and pressure buildup will begin earlier as a result. Transfer pump pressure The advanced parts and the advanced spring are all selected to provide precise cam movement to provide required injection timing advance. The system is adjustable by means of a trimmer screw to control preload on the advanced spring. On 4-cycle engines, the injection pump is operating at camshaft speed. Therefore, the engine timing change will be twice that of the pump. The governor mechanism utilized in the Stanadyne pump is the final component to be studied. The governor in most pumps is a variable speed type. It consists of the governor weight retainer, governor weights, thrust washer, thrust sleeve, governor arm, pivot shaft, linkage hook, throttle lever, and throttle shaft. The governor spring and idle spring pack ride on the guide stud. During operation at a fixed throttle setting, an increase in engine speed due to a decrease in load will cause the governor weights to generate greater centrifugal force. They pivot outward to drive the thrust sleeve forward. The thrust sleeve drives the bottom of the governor arm forward, and as the arm pivots about the pivot shaft, the upper end moves toward the rear to compress the governor spring, moving the linkage hook and metering valve to a reduced fuel position to maintain the selected engine speed. An increase in load upon the engine will cause the opposite effect. Under increasing load, engine speed will drop. A lower centrifugal force is generated by the weights, and the governor spring causes the weights to collapse. The governor arm pivots forward. The linkage hook and spring move the metering valve to permit more fuel to enter the pumping cylinder so that the engine generates more power to carry the additional load. Opening the throttle will have the same effect on the governor components as increasing load. However, the engine will now run faster due to a greater compressive force being applied to the governor spring. With the throttle in the idle position, a small spring in the idle spring pack is used to balance the governor weights at engine idle speed. The engine idle speed is adjusted with an external screw on the throttle lever, and the maximum engine speed or cutoff speed is adjusted with a high idle screw also on the throttle lever. Other types of governors are used in the Stanadyne pump, such as a min-max governor for automotive applications. However, the variable speed type is the most predominant. You have just seen a brief glimpse and explanation of the functioning of the various parts of the Stanadyne distributor pump. The function of each part has been explained, but it should be remembered that the pump is a very complex mechanism. Proper maintenance of injection equipment is of utmost importance. Repair of diesel system components can only be accomplished by experienced, factory-trained personnel working with special test equipment. Proper care and skilled repairs to the fuel injection system will guarantee its proper operation and continued long life. Produced by Stanadyne Diesel Systems, Hartford, Connecticut, USA.